Hello, my name is Bruce Drolen, and for the next 10 minutes I'll be giving you an overview of oscillating heat pipes, or OHPs, and discussing some of the key issues that remain in this field. I am a retired Boeing Senior Technical Fellow. While serving as an STF for Boeing, I was the company's thermal management focal. Most of my experience is in spacecraft thermal management, but I certainly branched out to other thermal issues across the company. Including my 3 years of consulting, post-retirement, I have 41 years of experience in this field. My interest in OHPs started in the early 1990s when they were first invented in Japan, and I've been actively working on their development and understanding of their operation and limits of performance since about 2010. The earliest OHPs, and many of those that appear in the academic literature, are comprised of small diameter tubing bent into a serpentine shape with the ends either sealed, a configuration called open, or connected to each other, called closed. The inner diameter is chosen such that a fluid charged into the device will span the diameter via capillary force, forming liquid slugs and vapor plugs. In more modern OHPs, a serpentine pattern of micro or mini channels are machined into a base layer. The channels are then closed out by hermetically joining a cover to this base layer to yield an enclosed serpentine channel. This channel is then cleaned and partially filled with working fluid, and then the device is sealed, capturing the fluid in the channel. This working fluid naturally forms into a discrete chain of liquid slugs and vapor bubbles or plugs. Flow begins in an OHP when heat is applied to a location or locations on the device. This causes liquid to evaporate, and the resulting expansion drives the adjacent liquid slug toward the colder region of the device called the condenser and back to the evaporator in the adjacent channel. Because of the large number of channels, the resulting motion of the slugs and plugs appears chaotic in nature, with flow reversals being common. When the wall superheat is sufficiently high, nucleation begins, which adds even more driving force to the flow and drives the thermal conductance to a much higher level. The heat transfer in OHPs is due to both latent and sensible heating. Review of the literature shows that there is disagreement over which of these dominate the net heat transfer. My colleague, John Allison, the thermal lead at AFRL Kirtland, graciously allowed me to present this chart of his with a few notes of my own at the bottom. John noticed the pattern in the application of new technologies to spacecraft thermal control. Heat is transported within the structure of the spacecraft and by radiative exchange between the surfaces. The radiation part of this path has changed some over the years with modification of surface coatings, but if we focus on transport in the structural elements, a pattern develops. From 1959 to 1979, all the heat transport within the body of the spacecraft was by conduction. In 1979, conventional capillary-driven heat pipes were first introduced into satellites. 20 years later, in 1999, loop heat pipes were introduced into satellite thermal systems, allowing the use of deployable radiators that effectively tripled the heat rejection area of the vehicle. I was one of the engineers that helped lead that charge. Last year, another 20 years later, OHPs were being integrated into operational systems, and 3 OHPs returned to Earth after operating well for 780 days in a flight experiment aboard the X-37B. So why are OHPs generating such interest? One important feature is that they operate better at high heat flux than they do at low heat flux. The net heat flux levels in today's electronics are growing very quickly, and a thermal device that is well suited to that need is a timely addition to the toolbox. The channels of the device that can be built directly into the structure of the thermal planes holding the circuit cards. They can also be built into the chassis of the electronics box, the structure separating the boxes from the radiator and into the radiator itself. This allows the structure of the spacecraft to be truly multifunctional. The heat spreading can be both 2-dimensional and 3-dimensional, rather than the typical 1D layout of today's heat pipe systems. OHPs have been proven to be relatively insensitive to operation against gravity, even under multi-G environments, so the operation of the system during 1G testing of the spacecraft is less of an issue than it is with today's heat pipe systems. Finally, they are relatively simple to manufacture once the processes are established. There are opportunities to make them out of materials that are CTE matched with electrical component materials such as silicon, so that the cooling can be brought even closer to the primary heat sources in the spacecraft. One of the things I've focused on over the last decade is to establish the limits of operation of OHPs. With my background in heat pipes, I worked to develop OHP limits of operation that are in some ways analogous to those shown in the lower left for conventional heat pipes. The model used for the limits development is a simple force balance on the liquid slug or chain of liquid slugs. I started with envisioning the things that could break down the slug. I see the slugs as pistons that are driven by the pressure head behind them. When the piston breaks down, say into an annulus, the pressure head has greater difficulty in driving the flow since the vapor can slip by the liquid. The bond number limit, appearing in the earliest of papers on OHPs, quantifies the temperature at which the fluid can no longer bridge the channel to form liquid slugs. The vapor inertia limit is set by the velocity and associated heat flow, where the vapor inertia force overcomes the capillary force in the meniscus of the liquid slug. The sonic limit is much like that in conventional heat pipes. It identifies the conditions whereby the fluid in the channels is moving at the speed of sound. The complication here was to estimate the speed of sound in a slug-plug geometry. The viscous limit identifies the heat load that would generate a given added temperature difference across the device in order to have sufficient pressure head to overcome the viscous losses. In truth, this isn't really a limit, but rather represents a particular viscous contour for a given delta T. The startup limit identifies the heat load at which nucleation would be predicted to occur. Below this limit, there can be flow in the OHP, but it is only driven by evaporation and condensation, so the velocity is much less aggressive. This leaves the swept length limit. OHPs have displayed an interesting behavior in tests. It has been shown that the limiting heat load agrees well with the vapor inertia limit if the heater is short. However, if the heater length is increased, the OHP will reach a point where it can no longer support the same heat load, i.e., reducing the heat flux by lengthening the heater can actually lead to dry out. By assuming that nucleation presents the driving force for the flow, the frequency of nucleation and the predicted flow velocity at the vapor inertia limit can be used to estimate a distance traveled between nucleation events. If that swept length becomes short relative to the length of the heater, the far end of the heater will experience dry out. This can be thought of as a comparison between the heater length and the amplitude of oscillation. Because OHPs are not capillary driven, there is no capillary limit. Nor is there a boiling limit in the typical sense, since OHPs work better when nucleate boiling starts. There is, of course, a boiling limit when the critical heat flux is reached, but that limit, as derived and applied to OHPs, is far above the others and does not really come into play. All of this is better described in the reference shown at the bottom of the chart, which was published in 2017 in AIAA's Journal of Thermophysics and Heat Transfer. So what are some of the key outstanding issues and questions in the understanding of OHPs? First, though I've stated that nucleation is the prime driver for OHPs that are operating at high thermal conductance, this is not a universally accepted statement. In fact, about 5 years ago, there were few of us that held that belief. The substantiation of this statement has grown stronger and is more widely accepted today, but further proof of this would go a long way toward establishing a better basis for models of OHP operation. I think of an OHP as a boiler in a confined space. As such, it is difficult to predict where and when the next bubble will form, since the process tends to be stochastic. Models that do not include nucleation, only evaporation and condensation, would only be useful for predicting the performance of OHPs operating below the startup limit where the thermal conductance is low. This may be academically interesting, but likely would not be useful for application. There remains significant debate as to whether latent heat or sensible cooling dominates the heat transfer in OHPs. In modeling that I've done, it appears that, quote, "it depends" is the best answer. There are temperatures and heat loads where latent heat dominates, and others where sensible cooling provided by the cool liquid slugs returning from the condenser is dominant. From my review of the literature, I think that the majority of the community sides with sensible cooling, but there remains significant debate. Some of the most detailed models include axially discretized liquid slugs and liquid films against the channel wall where the vapor plug exists. A key question there, and presently an adjustable parameter in those models, is the thickness of the liquid film in the vapor plug. It will be important to establish the physics of the flow in the OHP, including the thickness of the film left behind by a traversing liquid slug, especially in the heated and cooled locations of the OHP. As I stated on the previous chart, the fact that OHPs behave exactly the opposite from conventional heat pipes when presented with a longer evaporator at the same heat load is truly unusual. The swept length theory that I described earlier is my approach to explaining this unusual phenomenon. It has stood up to a number of different experimental tests, but there have been a few exceptions. It remains possible that there is some other, perhaps related explanation. There is some evidence that the transition from slug flow to annular flow occurs at lower vapor quality when heat flux is reduced. This could elicit a similar dryout when the heater is lengthened. So, though the swept length theory provides valuable insight, there remains opportunity for improvement in explaining this unusual phenomenon. Finally, in charging OHPs with working fluid, it has been seen that the thermal conductance improves as the fluid charge is diminished, within limits. Identification of the reason for this behavior, the optimal fill level for a given OHP configuration, and the minimum charge level to avoid are all active areas of research that could benefit from more insight. So, thank you for your attention, and I'd be happy to entertain any and all questions you might have.